Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. If you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. Okay, so let's start with this by opening the project. Let's compile. And there we go. So let's open the debugger to see where we left off. Now what I remember is that I'm sorry, oh Jesus Christ, the thing that we the thing that we did was that uh, okay, I believe we were playing around with we were trying to separate the instruction stream in two, which I believe it was the last thing we did, which yeah, like if you have an x64 instruction stream and an x86 instruction stream or i32. So that's the last thing we did, which we have these two streams. And yeah, so if we go here and see, well, what happens is that it's pretty much the same, just that we now don't allow to disassemble instructions that are not disassembled for the same let's say we have instructions for the up bytes and stuff like that. Well, let's say we have instructions for x86. Well, we don't expect it to have x64 instructions, which could be the case, you know. In fact, well, let's go while Visual Studio opens, which is going to take a while. We can just go and try to find something. Well, let me close all this. Or here, you know, it could possibly be, you know, can you mix? Well, it's not just can a compiler can you mix? I mean, you could, for example, let's say you have I mean, the most simple way to think about it is like, imagine you have an x64 stream, and in between you have x86 instructions. So it's just like thinking about, well, you have an instruction stream, which is just going serially, and then you have a jump instruction that jumps to the other block of, you know, of x64, but in between you're gonna have x86 that, you know, can be whatever, you know. Can you mix x86 instructions into the same, which is, I mean, it will make sense, you know, if you have a multi-platform a target multi-target platform, you have the necessity to, well, you can have like this fat binary, which you know, has all, it has the whole, it has for different platforms. Uh, it has the encoding for different platforms. Let's say it can be different sections. It can be different file options. You know, it's a little bit weird. You know, because you know we have fat binary. And you know, the interesting thing about fat binaries is that it's a whole thing by itself. You know, which you know, it can be different flavors. The compiler can, I mean, if the compiler or whatever compiler does um, spills out x86 and x64. You know, let's say we have a executable image with x86 and x64 code. There's not gonna be one way. Normally, well, when they, let's say a compiler like MSBC, it has like a, let's say it has a way. You know, it has a format into the way that it's gonna just print it out, which is a pfop format. So we can just say, well, for now, pfop format. Okay. So basically, what an RBA means is that, well, we already read this, but uh, just to make sure, we have that the RBA differs from the file pointer because of this random access memory. This is the loader puts all these sections in different ways. You can scramble them all together because that's the best thing it can do. Because normally, it depends on memory, how it is used and whatever. Then you have to break it out and do the scramble leg. So normally in the file, well, you normally have a contents thing, which you have. I mean, since we're reading from the file, we're gonna read it based upon the file pointer. But the RBA, it's also useful to us in the sense that we can use it as the output. Well, right now we haven't done that yet. But, this value right here, pretty much it's computed using the RBA. So we can use, let's say, I believe it uses the RBA just because, or no, it's not just the RBA, or probably it's not the RBA at all. Who knows? Probably it's the file pointer. But I mean, it's good to have the RBA, let's say, because the RBA is probably better in that sense, because the RBA is going to tell you where relative to the base address, which we don't know here. The loader is the one that decides that. So the loader is something, and then you just add the RBA, so you will have the scramble that you have in memory. The real thing, like how it's encoded, how it's put, which is nice. And pretty much that's the way to disassemble offsets, let's say, because you have to have that base, how it's going to be structured in load time, so you can then reconstruct, let's say, jump offsets, implicit calls, all this stuff. All those addresses, they are relative to sometimes, I mean most of the time, but it depends. They're relative to the instruction. So we have to make sure we have a correct RVA for each of them, So that's important. That's something we haven't tested yet, but it's let me put it there. Alright, so now that Visual Studio open, we can just see the thing. And there you go. So there you go. Uh, um, Let me think about this. So what to do now? So one of the things that we can do, let me think about this. So yeah, I mean, yeah, the thing that I wrote there, we can just, I mean, I was like trying, like thinking, could it be good to do it right now? And probably not, because I mean, we are like really just starting up with the disassembly process. So I want to see more of it, you know. We have to continue more the route of disassembling, and later on we can just, after once we're starting to join the pieces, then probably will be a better time to think about the RBAs and stuff, which is probably important, of course, because, and probably once we start like assembling calls and stuff like that, or well, disassembling calls for real, you know, disassembling calls and jumps, implicit jumps and stuff like that, you know, like we need to know the real offset where they are be jumping. Well, once we just don't care about the instruction itself, but we take care about the relationships to the other sections of code, then it would be a really nice thing to have to do, you know. So let's go back into here, and let me see. Well, we solved that. I mean, this is really important. Now we do care about if it's 64-bit mode or compatibility mode or whatever, you know. We think about it. Now we think about it, and you know, well, at least for the move instruction, all of them are valid on 64-bit mode. All of these tables, let's say. And yeah, they are just some of them that they're not. So it was a thing with the entry that we just say, hey, it's a 64-bit mode thing, you know, or not. So that's okay. So let's think about another instruction to disassemble now. we could think about the 1616, you know, which is just another way to say that's the same instruction, but it runs on 1616. It's valid on 64-bit mode and it's valid on compatibility, but you have to have an REX prefix, sorry, an operand size override prefix. And the 8s and stuff like that. You know, it's the same code. Well, let's do the 89 because we already have both of them. We just can do print the other one, let's say. So and we can make a switch, you know, like, hey, we're printing out 32 bits, let's say. So let me first disassemble. It's gonna be super simple. It's just gonna be the same thing, let's say. So what if we here over this 64 bits. Now let me think about this. Well, we can have, before doing the other thing, I'm gonna do the same instruction stream now without the REX, you know, so that we have move EAX. This is not possible. This REX. This is possible. It's 89. This 0. We have the 62D5. These are only, so that's okay. We have the 80X40. This is EAX FFF. Yeah, this is possible. FAT, FUCOM, fill, burn, resume. Line R, shield, add the AX. So pretty much all of them are. The only one that was only 64-bit was this one. So this can give out. And this is the only one of the instruction stream, which is the AAD. Where is the AAD? Here. And the bound instructions. So we can just do that, and we can just say, well, you know, I'm gonna have here the same opcode 0x0. But of course, we're gonna change this to so the only thing that is going to change now, is that well, let me do this so I can show. These instructions normally will be, well, I'll do it this way. Now, I mean, I'm not, yeah, I mean, this is could be a little bit confusing, but I'm just trying to see which ones should not be encoded and which ones should. So I just like on the probably it's not totally useful, but I just want to keep it there so I can see that, oh, okay, this is the thing that is not encoded, struct, whatever. So yeah. So let's do this. Probably it's not gonna happen. So yeah, I mean, you just print out the same stuff, and if I'm correct, it pretty it yeah, he disassembled it totally incorrect because we didn't make the shift. So if you think about it, we have a problem, because if you remember, well, no, this is correct, this is correct, this is correct, probably all is correct. So let's see what we well, I was assuming that it was going to do all bananas because we didn't do anything. We didn't add the 66 override prefix there. So let's see what we got. C bytes gonna do this, is gonna be something there, 66. Mandatory prefix. Oh, it thought it was okay, he thought it's a mandatory prefix, so that's the reason why it's gonna do this stuff. It's gonna think it's gonna 16, 32-bit, whatever. It's valid mnemonic entry, effect, begin operand construction, and everything is gonna be alright. So yeah, there you go. So we don't understand override prefixes right now, so that's the reason why we print the same instruction another time. So we can just play around with that and say that we now understand mandatory operand size override prefixes. And one way to do that, because if you think about it, well, the instruction could have a mandatory prefix present, or could have the 66 override prefix. So this is a tricky question. It's not something that we already know exactly how we can distinguish between them. So let's see. So we have 7 overrides, we have a bound prefix, which is another bound. Actually, this is interesting, this is bound. So, for example, for the bound, it's just if F2 prefix precedes an equal and return. It has some just special instructions that has that kind of thing, And then rep lock prefix using F0, H, rep and E, rep and C. These are another types of prefixes which are the same as it's F2 and F2. They apply only to some type of instructions, if they are used as this thing, Repeat if 0 or repeat if equals encoded F3H. So mandatory prefixes are also really instruction particular, or for example F3H is a mandatory prefix for puck count. We have so if we try to find, for example, this instruction, right now we have one with mandatory prefix, but it was not super, with just one it's not super representative. We have to have more. But for example, on the stream we have this 66 OF3A OF 61 OA 61 C1, which has this mandatory prefix and has this means that OF3A, it's a 3 byte table. OF mandatory, this is a main byte mod RAM, and the thing is the immediate. So the thing is that it was a PL line, because it works with SIMD. So normally SIMD instructions have that kind of thing, which has mandatory prefix and stuff. Also pop count. So let's see if I can see it. I gotta go. This is the same thing. No, this is REX. REX. For example, something that we could do is to expand the REX prefix, so we just fill it out completely, which I think, I mean, since that was the last thing we did, probably it's okay to do that now. Yeah, instead of going with the 66, I mean, which is something that we have to do, it's just that probably we should finish first REX, since we're already on the mood for REX. Let's do the whole REX stuff. So let's try with the REX now. I mean, for example, one thing we can try to do is to disassemble an instruction which has a different encoding for the REX prefixes. We know that well, the the encoding is the same for the REX, just that the representation of it, or the meaning that those bits go into, are different. You know, where do they go, where do they match and stuff. They're gonna be all different stuff. So register, we have 4 ways to do that. We can go for any one of them and try to think about how it's done. See the special cases as well, looking at the displacement. Jesus. Okay, so the direct memory offset moves in 64-bit mode. Direct memory offset forms of the move instruction are set to specify 64-bit immediate absolute. And we have the offsets and stuff. So immediates and stuff. Okay, so let's represent this a little bit more. So right now we already did, I believe, was one of these ones. I believe it was this one, because it was a register addressing. There was no memory operand. We're using rex.x, not used. Sorry. Using RMB. So X is not used because that's for SIB. The R can be for the rec, or it can only be for the rec, isn't it? Okay. So it's just for the rec. And B can be for the RM, the SIB base field, or the opcode rec field. Any of both. So this B goes to the RM, this B goes to the RM as well. This B goes to the base of the SIB, and this B goes to the rec. Okay, and this is different from 1.1. That's okay because it's not a register, it's another addressing form, it's extended, boom, SIB thing. And we have b rec b. Okay, so yeah, I mean, let's do all of them for the sake of it. So we can start with the memory one, which is probably the same, one of the simplest one. So we can say, well, I'm gonna put it to do there, to do, and I'm gonna say another 48 here with well, I say 48, but well, it has to be 48 because it's 4 and it has to be, well, it depends. If we use the operand size override prefix, it's gonna be REX. If we don't use it, but we have, for example, on the move, it was because REXW uses 64-bit operands, and if we want to use the extended opcodes, we only use REX, isn't it? Well, in the move instruction, it's not like super clear, but we can try to find out another one. So, for example, with the shifts, well, the shift's not gonna be, it has a 2-byte thing, so it's OFA4, OFA3, REXW, OFA4, OF blah 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 blah. So it has to be another instruction. REXR is ignored when model RAM specifies other registers. Okay. So if REXX modifies the base index field, that means that on the table the index is gonna be what? I mean, it's gonna use the extended registers to make this kind of scale thing, or what? Probably it is, because if you remember, where was that table? No, it was not here. This is floating point instructions, formats and encodings. You have the ARPL before format calculation. What do we have this? This is a move. This is, oh, this is the one. We have a table here. This one. Register codes associated with RBR, WR, DR. Okay. Indicate the lower 3 bits of the opcode bus used to encode the register operand. Okay, hold a second. In a 964-bit mode, the register code from 0 to 7 is set to the hexadecimal value of the opcode by. Okay, that's normal. In 64-bit mode indicates the 4-bit field of REXB. Oh, okay. An opcode 02 field encodes the register operand of instruction. Oh, okay. Huh? Oh, I see. I mean, why didn't say just like I was like, oh, so confused. it's joined together. I mean, we are seeing a 4-bit thing where we have well, yeah, I mean, it was good that they tell me that what was it, but yeah. So we have the same thing from 0 to the we have 3 bits that specify the register, and then on the 4-bit or the number 3, we have the bit for the REXP bit field. And yeah, so that means that we're gonna get, and this is the thing for Lincolns. So this is pretty much the thing, because it should be, this is the table, yeah, because this is the thing that if we use, that's the reason why we have REXP at first place, for the first place, we use REXP to extend the code so we can use R8, R9 through R15, and we can use them like with these codings, doors stuff, so that's the reason why we have those. So let's pretty much use those, to see how they are used and stuff like that. So let's try to, we can do the same move instruction, I guess. So probably, I mean, we can have the D0, or no, it was the 89 thing. So we have 0x48, 0x89, 0x0, and this is gonna have an extended, it's gonna be from memory, so the mother M is gonna change, and it's gonna change to, I don't know, let me see. We can say that we're gonna have a simple thing here, I don't know, it can be this 32, let's say, with let's say we have this one, so we have 010, and then from the rec we're gonna have we can have ECX 92, we can have 9A, we could we can assume something like the stack. We haven't used CBX, so we can use the base pointer from memory, and then how it's called, move like a EVP SP, something like that with an REX, but that's not possible. because well, if I want to use the extended things, because they are R8, R9, so we're not gonna use that thing, I guess. I mean, we want to use the registers, then it would be a memory thing, so it would be something like in fact, I can just try it. It's just like, this is our test code. We can see what's possible and what's not. So we're gonna move from, I don't know, to R15. We're gonna move, well, normally the best case scenario is R80, because yeah, and here we're gonna just use from EAX plus displacement 32, which for our case we're gonna say that we're gonna have this 32 dB toward something like that, and then move array t xp fucom sti1 and this thing is running, so that's the reason why couldn't end. So the assembler we have a vinculation, a linkage error, ADDR32 to this invalid. Is that because, let me see, on initializing buffer 25 69080H. For example, here we use the type defs that we can use as here, I believe. So and the problem is they're not the same size, but this is a door, isn't it? This is a door. It has to be well, let's let's say this. And this is the there you go. So this is oh, I forgot it. The word pointer. This is the way. My bad, my bad. Do we have to use large address aware stuff? We don't have that. exit process. How do you call it? Large address. But this has to be vinculation, isn't it? So we have to go to vinculation. This is the B. This is linker. And I can say large address over it tells compiler the complication supports addresses larger than 2 gigabytes. With large address aware to that effect. In the 64, this option is enabled by default. The 32-bit compilers large address now is enabled if large address aware is not otherwise specified on the linker line. So we have to use this, but this is a 64-bit compiler, isn't it? Do we need to use it? Are we linking? Are we building something in? Whoa. That is not 64-bit. It's 64-bit. Come on. Default 32, user 32, entry store. Yeah, we do that. Large address aware, let's say. What about that? Dude, oh, okay, my bad. So this ADDR32, I suppose that is the name that the assembler put to this 32 thing. I suppose. That's my guess. But I should not guess. I have to find out. So if I think we have on the test bill. No, we didn't. We need these ones. There we go. I don't care about that. So we have the listing, and then we have the types: core, double flow, long toward, pour, type, value, text, active, attribute length, public. Where is our type? We have this div32, this is the word type data, which has a value of blah. It doesn't tell me the name that put me. Exit process. So yeah, I don't see that thing. So it's just that it doesn't. Are you serious? Well, we're using beam resume stuff, so probably we can I don't know. Whoa, this was crazy. Why we have that thing? Cool. We have st1 door pointer EAX. Okay. For example, we're using here RID door pointer EAX blah 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 blah. And we are using EAX plus 3048. So you can see here we have 44, 67 probably is a number right prefix, 44 AB, so let's see. Oh my god. Okay. We're using AB with REX. So we're thinking about this way to do it from memory to R64. So this is correct. We have an AB with an REX. So that means that this 44 is going to be an address. Sorry, an REX, sorry. Which is with REXR. That means we are using REXR, which was the thing that we were trying to do. So on the R, on 80 we have 80, which is 32-bit address forms. With the modern by. So we have this one, EAX plus displacement, There you go. And we have RAD, that means this thing over here on the rec. So using the rec with RAB, that means that we have RAD, and then we are using the thing. So the interesting question here, well, and we have the displacement, of course, and I don't know why it's 40. I wrote it bad, I guess, but yeah, this is the displacement. And it goes 0 0 40 40 0 0. Okay, and that's pretty much it. See? Now this is an interesting part, the 67 thing. The 67 is an address size override prefix. That means that we needed to modify the address to use a 32-bit address size override, since we were using the other thing around, you know. So this is important, because if we want to do something like this, we need the address size, since remember that address size normally would be 64 bits, you know. Here we are not using REX. If we were using REX, then we would get something totally different, you know. But we cannot use REX on the memory displacement, so that's kind of a weird thing. We probably can. Wait, we probably can, isn't it? But it's just on the, no, because it's used on the RM, and it's used only. Look, if we're gonna do this kind of stuff, but we use the REX with R prefix, which right now we are using it on the R. On the the B, if we want to use it on the B, it can be used as well. Only that the memory thing I mean, it would be if we use like let's say we have this R9 the is that possible? Yes, it is. Oh, my bad. Okay, my bad. So now if we disassemble this, we can see what's going on. And let's say we where is it? Here we go. We have both of them. Both of them need the operands, the address size override prefix, since we are using the word as an operand. We have different. This is the REX prefix. This is 45, which is using B. Good. Now we're using B to be used on the RM field, and we are using R on the rec field. So we can use R extended opcodes there, extended register, sorry. And we use AB, the same opcode, main opcode. A1 is the mothering by. Now here we're using R9. That means that yeah, that's correct, because it has to be A1 because we are one shifted on the table on the mother and by. and this in the displacement is just the same. So that's the thing, you know. So that's interesting. That's kind of nice. And of course, I mean, if we can, I mean, we can even try. You know, it's not gonna be possible because, yeah, you know, it's not a thing. We cannot do this, you know. It would be just banana. It's possible? Are you serious? Oh my god. What's gonna happen? This was not possible. This was not possible. Well, probably it's possible because... Well, let me disassemble it. Oh my god. No. Here you go. So let's see what happens. There you go. No size supervised prefix, and the other thing is just the same. So yeah, the size supervised prefix is the one that changes there. Good. So yeah, it's possible. The thing or the problem would be if, well, at least on 64-bit mode. On 64-bit mode, we couldn't, or at least we shouldn't, do this. You know, this is not possible. In fact, since this is a displacement 32, this probably have to be this. One, two, three, four. Okay, that's by no means possible. Yeah, because we are on 64-bit mode, so this is not possible. So yeah, I mean that makes sense. But we can use R9. That's kind of cool. So the table extends to that, even though we don't have that. I mean, the table we don't see that. It's possible in 64-bit mode to do that. So that's good. That was nice to do. That was something that I wasn't expecting. So and yeah, because on the 16-bit mode we don't have that thing, see? We have to have px plus si. So we have R9A plus, well, it cannot be R9A, but, or well, let's see if we can do it. And some index RAW plus. So yeah, it has to be this. It's just not gonna be possible. Yeah, it's not gonna be possible. So yeah, that's okay. That's understandable. But this is kind of cool. So now we have expanded our options for the modern thing, and we can just do this, you know. And this is not gonna need. So that was the thing that, I mean. So let's use that in coding as well. So let me, well, oh, I'm sorry. Let me go here. So this is gonna be, first I'm gonna do the one without the operand size of our prefix, and then we can do the other. So we can just say this is gonna be 40. 44 0x8d USAD. $44 ABA0. And then a displacement, which is going to be our displacement that we decided to be there we go. So let's start with that, okay? So that would be 44 AB80 in fact, well, I'm gonna do bananas here. A B C D. Alright, so we can see, or 0 0 1 1 2 3. Yeah, that's good. Okay, so this is our next instruction. It's a move instruction which has a memory operand from the source moving up to the destination, which is a reg. We have the REX prefix with a R modifying the rec. So we're gonna have, this is gonna be, I'm gonna write here, it's gonna move R8 to oh yeah, and it doesn't has an, it has to be RAD. So this has to be RAD or RAD. Yeah, I mean I am writing it on uppercase letters because I don't know, I like it more. So RAD, and it's gonna be EAX plus displacement. It's gonna be 0 0 0 0 0 0. We don't have the edge, but whatever. We probably should have the edge, but yeah, we can think that about later. So this is our plan. Something like that should happen. Well, with the dwarf pointer thing here. So, and this is really super useful. Well, this is the MASM thing, which we can, yeah, I mean, we can do the same stuff, I guess. So we can just refer that we have an operand size of that thing. So yeah, probably we are gonna do that as well. So let's do that. And then the displacement is gonna be blah 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 blah. And then that's pretty much it, eh? This is the thing we should expect, okay? So the pointer reactive 4, okay. So let's go and do it. Let's go and do it. It's the same mnemonic, but it has another table, so we should add it as well. So let's go and do it here. it's just gonna be another move in here. It's gonna be it's a 1 byte table, isn't it? So it has to be here somewhere. It has to be a B. So we have this one, GBB, a B, and then we have whatever. This is another move. 8C, but whatever. So we have 8B with the 1 byte table, so we can just add it. This is move. This is gonna be called move 00 entry. This is gonna be move 01. Probably I can call it move a B entry. Move. I mean, the names doesn't matter here because they're gonna change totally. You know, because we have the A9 thing, so this is gonna be A9. Yeah, it doesn't matter. I'm gonna keep it like this. So this is gonna be 01 entry. There we go. And this is gonna be up table entries. The total entry can we have another RAM. Yes, we do. This is from this false. We're going from REX to model RAM. We're going the other way around. Now, even in that case, let me see the direction as well, so we can make sure we are doing it. This is for the codes, this is for the 1 byte, this is for the double. Where is the thing? Here. This is the move. Let me zoom a little bit. We have from memory to REX, so it has to be this 8. And this is A, B, that means the direction. So yeah, so and the width is the bit that defines it. So here the W bit is set, that means that we have a full extension. If it was a as we had before, like for example, yeah, like these ones, 8A, they have to be R8s. 8B have to be the whole thing. 8-9 have to be whatever. 8A has to be R8s. So yeah, because of the direction bit. So because of the W bit inside the opcode. So that's good to notice. Most of them has, if they have a this, I mean, if we see this pattern of that we have the 8s and 88, and then the complete sets of 16, 32, 64 on 89, that's a kind of a story, you know. That's the story. Okay. So this is gonna be false. The print count here is 2. Memory operand size, we don't care about that. Register operand size, we're gonna say then what do we set? We set effective, isn't it? Okay. Immediate size, invalid, strength, length, and this is working with the operation mode as well. So this is going to be the move string as well. It's just the same thing. And here working 64-bit and 32, I believe. We have 8-bit, 64. It's just valid on, well, yeah, because we have the whole stuff. Okay, so yeah, it's also valid on 32. So let's just keep it there. Okay, so pretty much the same thing you just see here. Yeah, the rect to mother RAM is the only thing that changes, and the operand count is the same. Okay. So we did that, and we have to add the byte. So here, 1, 2, 3, 4. There you go. There you go. There you go. We compile, and we have to add the entry here. And I think that's it, isn't it? We should have 5, of course. So it's counting 1, 2, 3, 4, 5. Yeah. Okay. Okay, so now we're ready. Let's see what we do here. We're gonna do bananas, if any. So let's see what happens. The C byte, it has to be, this is the REX 44. We don't have that. We don't have a mandatory prefix. We have a mandatory REX present. There's we do. So we modify the stuff, and C byte, we move past by there. So right now we are not using the W bit at all, or the other stuff at all. So that's something important to think about. And we get the mnemonic. We should get the same, I think. We have a move with a false here, and a true here, and a tree here, and there, invalid, invalid. We have an effective. Yeah, that's correct. Begin operand instruction, fetch memory operand. Alright, let's go in here. This is gonna go for the mod RAM, which is a memory operand in this case. There you go. We say, hey, you know, we're gonna happen to have this thing, which is a data size 32-bit displacement. We have that. We're gonna push string, and then we're gonna have SIB. We don't have SIB. Fetch register operand index size. It's gonna be 4. Okay. So let's see what happens here. And boom, this is gonna be a problem. Index, yeah, because the thing that we thought it was correct, now it's not correct. Okay, so okay, that's good to know. Yeah, because this is gonna go for RAX, but we want EAX, you know. So if you see here, we're gonna print RAX, which is not the case, but we're gonna change that in a moment. And then we're gonna go for the symbol, and then we're gonna go for this where we have a scale there. We do have a displacement, which is a whole thing there encoded. Displacement is 4. Okay, that's correct. There you go, that's correct. Push string to buffer, open size. Okay, it was almost there. We got to the fetch register opening. And here we're gonna say the effective operand size is gonna be 8. Okay, and the result is gonna be fetch register operand. Let's see. It's gonna go for REX as well, because we are not using the R bit. Okay, so the instruction is gonna look like that. Okay, it was a the first try, so that's good. And the other stuff will pretty much has to be the same, I guess. REX, RDX, FF0, ST0, ST1, FF4, X0, X01. So yeah, so let's do that change there, so we can just see the correct thing there. So the first thing I would like to see and to do is okay, so the thing is correct. Now we need to use the thing we had on the fetch memory operand, which was here, over here. We pass the index size, and the index size is gonna be normally 32-bit, but we said that if we pass how it was, if we have REX prefix, we change it. So probably the REX is not gonna be fetch register. If you remember, we're doing this stuff where we say, hey, we have an REX present, we just modify it. This is not gonna work anymore. So we want to do something better here for choosing the REX or not. Since it's the operand, no, hold a second. Hold me a second. Yeah, because that's the, where is it? No, that's what? Where? That's correct, because I was just getting confused. Hold me a second. Where is the encoding that we should expect? Here we go. So we were saying that we have R18 or pointer EAX plus F04, but this is not correct, because I just wrote it bad. We are looking for, because this is for the 67, we don't have the 67. So even though, let me write here so I can see it on the test lesson. We want this, yeah, we want that. because if we use that, of course this has to be something. There you go. So now if we disassemble, now we should see the thing that we were expecting. REX RID 44 AB80. Yeah, this is the thing we encoded. Now let me change this to, this is 4. I don't see the 44 there. Do you mean this? What about there? Well, I don't know why it's 4-4. It's not 4-4. I didn't code it 4-4. This is a 0. It's just pure zeros. And for the, yeah, the disabstand, it's a little bit weird, isn't it? Well, I mean that doesn't matter right now, but yeah, this is the thing. You know, we have RAX, we don't have the override prefix there. That's the reason why this is the thing that we are going. So that's correct. You know, the thing will be with the prefix that we have to. I mean, of course, we still have a problem, but it's not the problem right now. So the only problem right now we have to care about is to add in the RAD thing. You know, so so yeah, that's okay. So the thing that I was linking the thing. So let's go to REX person. Here we have to have a way to dissect it, you know, like give me the whole thing. Give me the whole, you know, give me the bits, you know. We can get the flags and just say, hey, you know, yeah, get the bits. Now I don't know if we have a function that will get the bits. We have this get bits. We have another get bits here. We have a lot of get bits, but yeah. So we have these get bits, which basically make some masks and stuff like that, which we can use, of course. This is something useful. We want a generic bit field expression with bigger than 321. Okay. This uses a bit with field result. Okay. And the value. Okay. Which, yeah, I mean, divides the prefix. I don't know what we were doing here. We can just get rid of all this stuff. Get byte size of operand type. Yeah, well, it doesn't matter. Get bits EagleFly. Well, for now, I mean, I can just make the masks, and then later we can just implement that. So for now, we can just do that. For now, we haven't even used anything about get bits. We have just make shapes and stuff like that, which we can in the future like compress that stuff if we are using a lot of shapes and stuff like that and masks. So, you know, our own, we can call it our own shape mask library. Yeah, I mean, even it sounds funny, it can be super useful. So uh, um, so we're gonna say, hey, we are gonna get the R bit. It's called the R bit. Yeah, the R bit is gonna be REX on C byte, shifted by it was the shifted by 2 and CX1. So this goes to the rec. That means that it has to be passed as along with these things. So probably I'm gonna pass the whole stuff. Now we're making the resolution. So I'm gonna make a struct here. Probably that's the thing. So I'm gonna say struct REX. Yeah, why not? REX result, REX fields, let's call it REX flags, let's call it. And it's just gonna have this, and then just move this. Oh my god, move this around, play around with this, you know. It's like REX flags. I'm gonna move it to here. And over here I'm gonna say EagleFly REX flags, REX flags. There we go. Here REX flags. Present. REX flags bit, and you know, probably in the future we can just get rid of this, but it doesn't matter. Yeah, we can just say that, and we can just say, well, we're gonna have the R bit, and here we're gonna say that where is it? Instead of passing this, I'm gonna just come pass the whole stuff there, and yeah. And this be that, and this of course has to be something different. It's it's gonna be EagleFly REX flags REX mm, um mm, I mean, we can use a pointer and say just this. Yeah, I don't know. I don't know. I mean, if this wouldn't work if we have a different frame of reference. If not, we will need to store it somewhere because we're using it. We're storing it on the stack right now. So you just have to make sure that the yeah. So probably make a copy of it. We can make a copy of it, and I prefer it to be a copy. Yeah. Why not? Let's make a copy of it. So we just copy the whole block there, and right now we don't care because the whole thing is the same stack, but yeah, whatever. Okay. So yeah, that's the thing. Now that was the nice thing about it, that we don't have a pointer to it, so we can just notify the whole state. And then we just say REX here. It's gonna be 0. And where is the other stuff? REX. Is it can, but now we can assert it because we have to be passed an REX. And then of course we have to add it. This is going to be EagleFly REX flags REX. This is a pointer, and there you go. This is this. Alright, so there you go. Now we have to just add the idea that we have that bit over there. So since this is for the rec, we're gonna say that well, I don't know if we even add them to the table. Yes, we do. R8, R9, R10, R11, R12, R13, R14, R15. So we can just say REX R bit we can do that. And yeah, I mean, of course, probably in the future we want to do something better, but this probably is going to do the job for now. Super wonky, I know. REX, what's going on here? REX, disassemble stay, REX orbit. There you go. There you go. So let's see what happens. You know, it was a super little change there. So we're gonna say that we have an REX, we have an orbit, we have an orbit that's true, and then we're gonna move along. You know, we're gonna get the entry. This is a move which has false there, so we can just say, hey, that's correct. Begin operand extraction, fetch memory operand. The mem buffer has to. It was. Oh, because we're using, yeah. Okay, so we have to change that as well. And this has to be R8 as well. Yeah, this was R8 and the other was RAX. Okay, so finally we have R8 plus R blah blah blah. Okay, so we can change that pretty easily. So that probably tells me that this shouldn't be here and this should be here on the one we used for the rec, so that we make the resolution here. We have the effective operand size. We can also say that so that probably tells me yeah, this is not global. So we can just say these. Yeah, we can make the resolution here as well. Whenever we saw the index, yeah, this has to. This doesn't be here. This is gonna be here. So if fetch our field. Row index is gonna be blah, else it's gonna be blah. So this is gonna be here. Or fetch our field. Mm. I mean, this is the only thing that has to be happening if the RX so there should be a simpler way to do this, but I don't see it right now. So this is gonna be like this. So here we can just say the same thing we were doing before, which is fetch RM fill. Now if it's REX prism, we're gonna get the index from here, and this is the same, and from here. And and yeah, so here we will need to have a way to say it's because, well, I mean, we can use the same stuff here, you know, like if we're fetching from the mother rec for the REX. Let me use a stop function here, so we can start collapsing this in line. Now the reason that I was like thinking, well, we need the modern bytes because we have the row index and stuff, which that's okay. You know, all this stuff is gonna be there. The only thing is that whenever we have the REX prism, we have to choose a different value. But that's the only case. That's the only thing. So that's the reason why I say, well, this is the row index and stuff. I mean, this doesn't matter, it's not compressed, but the bit scan reverse probably, we can get rid of the bit scan reverse at all because we don't need it. We can say, instead of doing this, I'm gonna do something better. I'm gonna get rid of that. I'm gonna say that I want to move this and this, then, and I'm gonna say this. I'm gonna call this size now. It's not effective operand size anymore because it can be an address. Now I want to pass yeah, and we pretty much can collapse all this stuff. this is gonna be cool now. Well, we're not gonna do this. We can do that. And we can say Now we can get the entry itself, probably. And we can collapse the whole stopper. It just depends on the functionality, of course. Right now we just don't have a lot of things. I mean, there's no reason why not to do this. So let's do it. I mean, the names, yeah, I mean, we have to think a lot about the names itself, because the names, I mean, they can be ad hoc and be placed on the same entry, or we can have a name stable independent. Which I prefer the name stable independent, because it's simpler and it doesn't, I mean, the layout of the thing, it would be a pointer itself, so yeah. I mean, in any other case it would be the same pointer, but you know, you got me the point. So yeah, the result is gonna be the name, whatever name. I can get rid of this. Let's just say that we return that. We have rec name scan. We don't need this anymore. The rex is gonna be rec. EagleFly rec. Where we say are you serious, this is a problem? Now let me change that as well, because that's going to be a problem. Data type, EagleFly up. So yeah, I mean that's the whole thing. So this is a problem. Let me compile again. Come over from car to unit 32. So we're just gonna say, hey, it's gonna be get register. Name. Get register entry. Yeah. And then even though we don't need this anymore, we don't need this anymore. Well, we don't need anything of this, is it? I mean the tables, I mean the floating point, the information can be there as well. And if it comes from the other side, you know, because it's ST0, ST1, it can just be done the same way, you know. You can just get the register name, and that's all. Probably I mean, we need a type here, but type it can be floating point data. Yeah, okay, now see, we can have this. I can use this and then say something like that. Yeah, I like that. I mean, I want to get rid of this, so we just need to do this, eh? Because before, well, we needed to pass that thing. We can make the resolution with this. Now we're gonna pass some flags. We're gonna pass if it's a floating point thing. If it's a floating point thing, it's something that can also be encoded like that, you know. If it was not a floating point, if it was another kind of cases, then we will need to pass the REX, which is the only thing. Yeah, and then we just do that. and then we this, and then we just don't do that at all, and we probably also want to pass the mother and bytes. And even though, I mean, we can pass the REX itself. Which can be that, I guess. I don't know if we want a pointer to it. Yeah, we can pass it like that. And that's all she said. Right now I'm gonna do that. I'm gonna say that, let me just pass the buffer cam, buffer SAS plus string length plus, where is the thing? So yeah, I mean, where is it? The begin thing. We have a problem here. So let's put the entry with the rect type. Entry session. And so whenever we initialize this stuff, begin operand extraction. We're gonna pass, instead of this, we're gonna pass that. And then it's gonna be the same. Now on the disassemble, instead of having REX flags, we're gonna have an REX pointer, which I'm gonna call it REX by because I think it's better if we call it that way. So I'm gonna call it REX by go. And well, this is gonna be rec name stable. And of course, this here is where we're gonna do the different stuff here. But for now, I'm gonna skip it. I'm gonna do change in register table initializer. We don't have this anymore. This we don't have it anymore. This we don't have it anymore. And REX byte is gonna be, oh my god. REX byte. Boom. There you go. So it's not gonna do, I mean, if we run this, it's just gonna do bananas. But I'm gonna do the change on the next stream because I gotta go. But we hope that we can, I mean, we just make that little transformation. We saw that how we want this to be looked at. You know, we just get the register name and we pass the necessary stuff for it to be resolved. So it's not like, I mean, we have to change the table entries so that they also match they have the rec type as well, which is not something that we have right now. I can do that. I'm gonna just put it here. That's something that I should do. So for example, this thing right here, and That's all, isn't it? Well, I'm gonna put it to here. There you go. Okay. I can even put it like this. You are here. There you go. So yeah. So with that change, I mean, we pretty much have a nice transformation there, so we can just get the register and make the solution there. So yeah, I mean, I prefer that way and have this stepping of the REX resolution onto the last part. It's just instead of making the API resolve that thing and get passes and flags, which I think it was a little bit wonky. So yeah. So please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. If you have any questions, please post them on relative to the thing that we did on the session. In this case, to the thing we did today. And yeah. So thank you very much for coming, and I will see you all on the next stream. Take care.